Hi there. I'm going to present to you today on predicting combat outcomes in Total War. This is one system of Total War that uses machine learning to understand combat outcomes. And we're going to try to share some of the technical challenges along the way and things that we've done to improve the model. So before I start, I'd like to say a big thank you to all the people that's involved. It's not just myself and Miguel here, but there's a range of people from QA, leadership, production, programming, and design that have been involved. And it's this collaborative effort from all these people to get this machine learning project over the line. But a bit about a few members of us here. We got Dugu, who's the R&D director at Creative Assembly. And she's been one of the masterminds behind this project and very influential in getting people aligned and getting decisions made. And we have Miguel here, who's the senior technical designer, who knows a plethora of knowledge about Total War and has really been influential in designing how this works. And myself, James. So I'm the machine learning engineer who's been helping build the pipeline and get all the data involved to build a model and train that model. And we're all delighted to share what we've done so far. A bit about Creative Assembly. So Creative Assembly is a UK game studio. We're based in Horsham, UK, and also in Sofia, Bulgaria. We have been mainly working on the Total War franchise and the game Alien Isolation. And we're proud to have a couple of unannounced projects in Total War today. But yeah, Total War has been around for the last 25 years. We're proud to celebrate our 25th anniversary. And it's usually Total War games are set up between a fantasy game and a historical game. And we try to be as authentic as possible in the genre or IP that we're playing in. And we do this by developing our own proprietary game engine. Yep.
Yeah, now, so in case anybody of you doesn't know how Total War plays or what it's about, and also to give you more context about what this big ops system actually is and does and how does it fit into our game, I'm going to explain a little bit about the two major parts that the game is comprised of. On one hand, we have a turn-based campaign, which can be classified as an empire building game. There is a large map divided into territories with cities and towns. And as the player, you control a faction who has control over some of these regions, and you have your own armies as well that you can move around the map. And usually, everybody else that you see in the map is your enemy. Your goal is world domination through either bloodshed or diplomacy, primarily bloodshed. And to achieve this, you have to use your resources to improve your towns, to get more economy, to get more and better troops over time. With these armies, you can move them around the map, and that allows you to either attack the enemy or the enemy towns as well. How this works later on, here we have a screenshot of you and an enemy army, and there are two ways you can actually solve these battles. One is using the autoresolver. This is an algorithm that will check both armies. I will run an abstracted simulation version of it. And at the end of it, it will tell, okay, actually you have a close victory, but it doesn't tell you like the full image. So some of your units will die, some of the enemy units will die. And under the hood, this is used as well by the campaign AI because when it tries to think, okay, what is my army going to do against enemy armies? So it will use this autoresolver thingy. Yeah, one important bit as well is like, okay, we have these two armies fighting each other. One part of how this algorithm works is that figuring out what happens when two units actually fight each other. And this is what we call the Battle Combat Outcome Predictor, BCOP for short. Now, if we actually play a battle, you can play them by yourself. And this is the other major part of how Total War works. There are real-time grand scale, so we are leaving the turn base only for the campaign. And you can have up to 20 units, which you can see on the bottom bar. And each unit is actually made of up to 150 entities or soldiers, maybe even more. Some of these can be from like just a human with a sword or a spear, very traditional. Or if we go to these fantasy realms like the Total War Warhammer 3, we have demons, dragons, trolls, pick your poison. Each of these units as well are simulated. Each of these entities that you see, we fully simulate their behavior of running, moving around, attacking, defending. We simulate every projectile that you see fire. We simulate the behaviors, the collisions. So it is pretty important for us that with all of this simulation, the game runs smoothly, performant. And of course, while all of this happens, you fight against an AI most of the time, unless you're playing multiplayer. So as in the same way, when you are making decisions of where do I move my units to fight, what do they do? If I move this here, is this a good strategy? The AI has a similar thought process. And one of the major tools that the AI uses to figure out if their actions or their plans are going to be correct is again using this VCOP calculation. So at the end of the day, we need like some way to be able to predict or know what happens when two units are going to fight each other. Yeah, usually this is not in movement, but yeah, we have plenty of different units in there. So yeah, as I was saying, I want to bring your attention on these two important parts. We have the autoresolver and the battle AI. The autoresolver is both used by the player in case they want to skip the battle, and also by the campaign AI. So every turn, every AI in the game will use this tool to figure out how their armies perform against enemy armies. Alternatively, we also have the battle AI, which in runtime, like every few seconds or even every few milliseconds, it keeps constantly checking, okay, if I move my units to the bridge or if I move my units to the wall, are they gonna win? Are they going to lose? So we need to make both systems at the end of the day use this prediction. So what we need at the end of the day, and what we currently have implemented through like standard algorithms, is this battle combat outcome resolver, which at the end of the day is just, hey, we have two units, just what happens if they fight each other? At the end of the day, this is what we are trying, this is what we've solved with machine learning, and we're going to go in depth for this presentation. We need a good estimation, because again, if this estimation is wrong, then the AI will make wrong assumptions and the whole thing falls apart. So we need a good estimation of the combat outcome of two units fighting each other. And by outcome, what I mean is, okay, we have two units with full HP, we have 100 soldiers, 100 samurais versus 100 Roman legionnaires. Who wins? How much HP do they have at the end of this fight? How many soldiers are actually standing? And who runs away first? Yeah.
So how do we go about getting this good estimate? Well, before we even jump there, there's some background information that we need. Firstly, we're working with the Total War game engine, and this provides us a proprietary software like our own databases, our CI and our CD that we have to use. We also have a variety of different entities or troops in Warhammer 3, 270 factions alone in Immortal Empires. And this model has to be fast. It has to be able to run in both our battle AI and our autoresolver, as Miguel has mentioned. But last but not least, it has to work. It has to be accurate. It has to be able to predict these combat outcomes well, and it has to be able so that design team wants to adapt things with that. It has to be tweakable so that the design team can change bits of it. So how can we go about doing this? Well, one of the first approaches that we've looked in, and actually Total War has used for many years, it's battle-tested code, but has developed problems over the time, is using a heuristic approach. Can we develop as many rules as possible to simulate these combat outcomes? And this is good because it's fast and easy to resolve in our code. But it does create a lot of edge cases, especially given the number of Total War games that we have, and we're moving from fantasy to historical games. This system becomes difficult and challenging to maintain over time. The other approach is, can we collect data from players? From players' data, can we learn, from this telemetry data, can we learn how battles are played in order to predict the combat outcomes? But once this is a bit of a chicken and egg scenario because we need this system to be ready prior to launch. And so we're always facing checks that we need to make, and how do we get this ready before it's launched? So what we decided to do was, can we simulate enough of this data from the Total War engine? And I think this is good because it allows a fully controllable setup for us. We don't have to worry about different data sets. We can just specify which units we want to train on. We can divide the map into multiple sectors so that we can have these different units fighting. And we can provide accurate ground truth, accurate labels of our data sets. There is some disadvantages though. It might not be representative of the real player's data. And there's a lot of retraining that we might have to do to get the model and the simulation working to generate that data. So there's a lot of validation that we have to do along the way. What does this look like? Well, it looks like this, where two units are engaging in our simulation environment. But we actually divide this map up into multiple areas. So we have more than two units fighting. We can have as many units as we want to train on. And then once we have this training data, we can start following the kind of standard machine learning flow where we are looking at that data generation. We're cleaning that data so it doesn't have any anomalies in it. We're creating meaningful features from that training data. And we're designing models now from that data set in order to validate it.
Now, I'll preface this by saying that despite showing like Warhammer 3 images and previous Total War games, this is not actually implemented in those games. This will be used in future Total War games. But of course, they have not been announced, so Warhammer 3 it is. Now, where does this start? Okay, we have the idea, we know what we want to do. It always starts with the game designer. The most important thing of this model is being able to understand the rules of our battles, right? We wanted to understand how armor interacts with attack, what happens when a ranged unit attacks a melee unit. So we need to make sure that we build a list of all these possible units, and we need to make sure that we have the range of all the possible stats. Once we have this list of units, we will pass that and process through a tool, and then we'll build up all the matchups and then we run through the engine. But going into a little bit more detail, we already have like an automatic system that will, again, once the designer plugs in what they want to simulate, we can define as well all the context because, of course, soldiers with swords will be very good at melee versus melee, but we also need to know when the archers are going to be good. And we also have situations where melee units can run and charge into ranged units. We need to separate all these cases and make sure we simulate every possible interaction so the model understands all these possible scenarios. Last but not least, because all of these are running in engine, like we run the game and we get actual results and simulation from the game. This is not like an abstract thing or a third party. The good thing, we upload all the results, like, oh cool, 2 units have fought, this is the end result. That gets uploaded to a database, and then we can start using that data later on. This is the actual tool that we use, so we can build a set of units. We have different parameters to make sure the combination of units are put at different distances, maybe they have different HP thresholds at the start. So we want to throw as much randomness as possible to this model to make sure it can learn not only when the units are at full HP and the conditions are perfect, but also when we can encounter situations that the players will actually face when they play by themselves. And yeah, what turns out, we have a lot of content in the game. So we started to say, okay, we want to cover all the possible, we want the dragons, we want to know what happens with the generals. Well, that made 200, I can't even say the number, 250,000 possible combinations. Thankfully, we realized that we actually don't need like all these matchups. We only need the most important key of them, and we need to make sure that we cover again this range of like, cool, we have armor in our game, and that armor goes from 500 to 50. As long as we have like some key pointers in between to make sure the model has with range, that's enough. The other thing that we've done, instead of having, like you saw in the image before, 2 units fighting on a map, we are trying to put as many combinations as possible. So that cuts the number by 16 times. Additionally, we not only have one computer running these battles, we can have multiple PCs running at once. So that cuts even more the amount of simulations we need. Thankfully as well, we've automated this process. Otherwise, we had to run this manually, create the list of units manually, feed that to the PCs. That takes a lot of time. And if we don't iterate fast enough, this will take even longer to develop. So yeah, all of the like uploading, creating the test, distributing to the PCs is automated. Now, what input do we care about? If you are trying to do a machine learning model for your game, this is probably the hardest thing to do. In our case, we knew that we wanted to know about the final HP of the units, how many soldiers are left, and who lost and who wins. And for that, anything related to combat was one of the stats that we wanted to care about. But of course, we have around 50 stats or so. So we started with a very small selection and added more as we were able to get a model that understands like the very basics of our game. We also have interesting idiosyncrasies in our game. So we have arrows, right? The arrow shoots the unit, and that means the arrows will fall on like more or less all the soldiers at once, blanketing the unit. This means that the unit will lose HP, but no soldiers themselves die, because they still have some HP remaining. And because no entities die, this means the damage that that unit can output when it engages, it doesn't change that much. On the other hand, we have these guys that have shotguns. These are dwarf blunderbusses. And because they flat fire most of the times, that means the soldiers in front will take most of the damage. So they usually die. So sometimes a unit of archers and a unit of these guys can do the same amount of damage. But because these actually kill soldiers on the first volley, that means the performance of the other unit changes. And we have a few more examples of situations like this that we need to make sure the model catches and understands about this. Because later on, when we want to auto-resolve a battle, it is calculating and doing relationships between all these units when they fight each other. So we need to make sure this simulation is actually translated into our game. Additionally, at least one of the benefits is because this is based on numbers and stats, we have a magical ability that increases or improves your units. If the number falls again within the calculations, the model can already predict, oh, okay, this is now stronger now, so it will perform better. Then it's like, cool, we have our database, we have already run our numbers, we have our thousands of simulations in there. The next bit is we have some bit of Python code to process and build the actual model. And before that, we do some cleanup as well on the data to make sure it's legit, which James will talk about.
Okay, so let's take a step back. So what we have on the left side here is some representation of our battle. We have the unit's strength, his attacks, his charge bonus, his tier, and other unit information that are not mentioned there. But we also have a battle context. So things like the encounter type. Is it melee versus melee? Is it ranged versus ranged? How far away are the two units? And which unit is really the attacker or the defender? That forms our representation of the data that we're collecting about whether or not these two units should win. And on the other side of this, we want to get things like the battle outcome, victory or defeat, the HP percentage for unit 1 and the unit 2, the troops percentage for each unit, and how long did that combat take, so that we can give this back to the battle AI, give this back to the autoresolver. And it would love to be simple to just whack this in a machine learning model, but it does take a little bit of tweaks along the way to make this trainable. So I'm going to talk about 5 of the tweaks that we've made that have improved our performance of this model over time. The first one is pre-processing data and things like setting up the machines correctly. So as Miguel said, we can parallelize as many of these machines as possible, but we need to make sure that they're running the same game build. And this game build, as you know, changes very frequently within game production. We also need to make sure that the data that it's producing is clean. So we do things like removing extremely short battles, taking any contamination or filtering from other battles that are happening nearby, and also scaling continuous variables. So what we're trying to do is we're trying to remove all the anomalies of this data set. Also, the second thing is forging features or feature engineering, which can improve the performance of the model. The first one that we found worked effectively was looking at weapon damage. So in Total War, a unit can have so many ranged weapons. And so we had to teach the model to learn these multiple weapons, either by combining them into one, or teach the model about individual siege weapons, which perform differently than other units. Secondly, we had to encode the different encounter types. So all of the melee versus melee, range versus range, melee versus range were one hot encoded to represent each of the battles. And this helped us with validation and testing as well. And lastly, the dynamic data, things that change. So your HP can be reduced, your morale can be reduced during the battle. And so this data, we found it very useful to take ratios of Unit 1 and Unit 2. One of the challenges as well we faced was with invariant data. So this meant that if Unit 1 versus Unit 2, the answer should be the same as Unit 2 versus Unit 1. This didn't happen outside the box. We had to make sure that we tested Unit 1 versus Unit 2, had a look at the inverse prediction of that, and Unit 2 versus Unit 1 to see if they were the same result. What we tried to do was input data augmentation to make sure that we were getting both the Unit 1 versus Unit 2, but the inverse battles as well. And model design, which actually usually is a smaller part for this whole machine learning project. We picked two models. One was looking at a multitask learning approach, where we have to learn each of task 1, task 2, and task 3, and we have this kind of shared layer. We found that this actually didn't work as well as if we had a more simpler approach, Model 1 and Model 2, where Model 1 learns the initial victory and defeat, and Model 2 learns by how much they lose, so how much of their HP was left over. And lastly, I'll say about evaluation metrics. So we can talk about precision, recall, and how many of the positive predictive values were correct. We could also look at network 2 and look at the initial, look at mean squared error and visualize these. But really the key metric that we were working towards is how does my game designer and programmer think? How does it feel towards the game? How does it feel authentic when I'm playing these results? And so lastly, these are some of our latest results. This is still a work in progress. We're still tweaking this behind the scenes because we're looking for future Total War titles, but we can already see a good trend towards predicting combat outcomes.
And cool, now that we have our model, it works. How do we put that in the game, right? That's the last step, deployment. So for that, on one hand, this is built in PyTorch, by the way, and then we try to use Torch for the C++ integration, since we have a custom engine. Didn't work out, so we are using Onyx instead. And yeah, additionally, we have a database because once we have this model along, it's not only like a file and you put it and that's it. We have some input data deviation parameters that we need to put along it. For that, we have a database, we can set up all of that nicely. And again, all of this process of putting the variables that we need and even copying the game model files is automated by another tool. So we don't even have to be aware, or we remove the human error from like copying database and lots of numbers for every parameter. Additionally, this runs on the CPU and it's quite fast. We need to make sure this is very performant because it will be called a lot of times for both the battle, in the middle of battle, and every time you like end a turn and the campaign AIs are like simulating what and figuring out what they are going to do. For that reason specifically, we did implement batch calling as well, and that allows us, like to give you some example, because we have 20 versus 20 units in one battle, that's 400 different matchup combinations. So that means instead of doing 400 calls to like the API and the Onyx system, we can do one single with all 400 combinations in, and then we get all 400 combinations out. And turns out this is more performant, and I believe the main reason was the overhead of calling Onyx over C++. So yeah, if you're trying to do this, investigate batch calls, is very good. What you see now in game, this is as well in-GUI debug interfaces that we have. So we can actually run the game, get some units in a battle, and then click on them. And that's actually actual prediction and predicted HP remaining values from different units, a different set of units. And again, we can click on every unit, we can get them to fight and see how these numbers work up. One interesting thing as well, because the model is made on a machine learning, this model is going to be deterministic, and that's very important because battle has to be deterministic if we want it to be able to work in multiplayer. We need to make sure that this model is as well, so battle AI can replicate the decisions that it makes. One downside is actually your battles are not deterministic. If you play the same battle 2 times with the same set of units, sometimes because of the simulation of it, the nature of the randomness when they attack and defend, you can get different results. So most of the time when it's okay, it's elephants versus a peasant, right? The elephant is gonna win, that's no problem on the prediction. The issue comes when it's very tight pairings, and sometimes the same unit can win or lose by very thin margins. And one of the downsides, or one of the keys, is that we have to take that, and it's fine. Because at the end of the day, the breadth and the difference in these predictions will come from the player's experiences. They won't always have the same combination of units to fight different armies. So it's okay that this is deterministic and it doesn't fully follow our simulation, and we cannot actually simulate with the model. But to be fair, the previous autoresolver algorithms weren't doing that either. We were always trying to get a deterministic simulation of what happens when these 2 units fight. As well, once we have the model, the benefit as well is we can run it without the game because we still have all our databases and all our numbers. We have a nice dashboard that allows us to see okay, what is this model actually predicting? This is very convenient because it allows us to set up what I call canaries, which is, okay, our game, let's think that it's rock, paper, scissors, and that rocks always beat scissors, right? What this allows us to do is okay, find out if any scissors is beating rock. That should not happen. That's a big mistake. And because we know our data and we know okay, swordsmen are the rocks, archers are the scissors, they should always be beating them. We can keep building a list of different matchups that we know should always be right. And that helps tremendously because that means I don't even need to run the game to see if the model is good enough. We could keep, again, there is a million topics on this. Feel free to ask us later. But I wanted to finish with some takeaways. First off, prioritizing what you want out of machine learning model is very important. Figure out what you want this piece of technology to do for you. What is the problem that you are trying to solve? It took us a very long time to figure out, these are the stats we actually care about, like melee defense, melee attack, and range attack. And starting with very small subset of parameters is even better because you can always expand and make it large later. But if you don't get your core right at the beginning, you're going to be roaming around the problem, beating around the bush. Automating, as many of the possible steps of cool, I want to run some simulation, get that data, process it, build the model, put that into the game. Please try to automate as much as possible of these steps. Otherwise, your iteration times are going to be 2-3 days. And if you want to figure out what went wrong, the leaner you are and the faster you are, the better. And this helps a lot. Also, this takes a massive effort from a lot of people, as James mentioned at the beginning, QA, production, design, programming, IT to set up the PCs and that. It's a large investment at the beginning, but now that we have it running and we know it works, and because we've taken the effort as well of making sure it's compatible with any features of our game, it's gonna save us way more time in the long run. So it does pay off 100-fold for the future. One or some limitations to be aware of. So our game is very complicated, right? In the fantasy version, we have flying units, turrets, we have magic as well. Every time you want to teach the model about a new concept, you have to go in and like make a new version of it. It's not going to be able to differentiate between the blunderbusses and the archers unless you tell it about it. And like in the same way we've differentiated with the booleans between melee versus melee and range versus range, the model knows what you teach it about. The good thing is not all of these features have a high impact on the prediction. So you can definitely prioritize what you think is most important for the prediction and then ignore the rest. Last but not least, yeah, it can niche break sometimes. So let's say, cool, you've added your content, you have a thing with 500 armor, next DLC comes in, you now have something with 1,000 armor. Yeah, that's gonna break. So you will have to go in again and teach it about all of these new concepts by making sure you have this new unit introduced into your tests and then make a new model out of it. There are ways to mitigate this by making like dummy units that actually have a larger range than your units, like giving you more breathing room. But again, it's a cost of what you need now versus how much you want to invest in the maintenance. And that's it. Thank you so much. Feel free to discuss some questions.